Well, if there is no further questions or comments for this group, uh, I would go ahead and introduce our next group of students and also the last group of students for today. Um, this group uh, is working on a project titled Cyclic volumetric study of nickel coated 3D electrode for hydrogen production. So the two students working on the projects are Babaka and Lofo, and their supervisor is Dr. Tiagi. Um, and Babaka and Lofo, are you ready to share your slides? Okay, I can see it now.
Yes, sir.
Okay, if you're ready, you can go ahead and start your presentation.
All right. Are you ready, Nuffle?
Yeah, I'm ready.
All right. Good afternoon, everyone. My name is Babu Karandoy. Uh,
And my name is Nufu Wadabo.
and we're here to present our senior project that details the cyclic voltammetry study of nickel-coated 3D printed metal electrodes for hydrogen production. Our main objective for this project is to generate hydrogen using nickel-coated 3D printed metal electrodes and to quantify the volumetric rate of hydrogen generated. In other words, we want to experience their reduction or an oxidation reaction through cyclic voltammetry. Fossil fuels are natural fuels formed from geological remains of living organisms. And this can be spread across millennia and millennia. And across that time, humans have been increasingly dependent on the benefits offered to us by fossil fuels. However, this comes at a price. That's because fossil fuels are carbonic in nature. They produce carbon, which is a greenhouse gas, and contribute to global warming.
So as we can see, few fossil fuel have so many environmental issue, and the availability is decreasing. So we have a limit on the supply on fossil fuel. So our motivation is to find a new alternative to fossil fuel, and we looked at wind, and what the problem with wind is that it is limited. It's only applicable mainly in agriculture because it is stationary, and also we have hydropower, which is using water like dam, for instance, to create power for um, agriculture as well. And also we have a solar. But for the problem with solar is with storage, we cannot store the energy efficiently to be used in all application, human application as automobile and for example. So the best alternative is hydrogen because it is abundant and we can store it efficiently and also apply it to any type of field and human use. So our main idea is to use 3D printed electrode for hydrogen generation, which will streamline our hydrogen production and give us more leeway. Next slide. Next slide.
For our methods, as Nofu just mentioned, we're trying to print 3D electrodes in order to streamline the hydrogen generation process, and this can be done through additive manufacturing. This is often seen as the future of production and manufacturing, and it's also more commonly known as 3D printing. And for our project, it has the potential to be used as an electrode. Why? Because researchers can easily develop any prototypes and materials. I think you've seen this in the last two or three, well, all the presentations. But you can build prototypes for testing within 24 hours easily. And this is a significant breakthrough in material research. However, 3D printed materials, especially metals, are often produced with defects. I believe in the last presentation, Samba said his resin material had was extremely rough. This is increased for metal material, uh, and these defects can be manifested in the form of surface roughness, decreased adhesivity, and poor conductivity. And those defects are the main reason why any additively manufactured material cannot just be pushed into production. It has to go through post-production. Um, this is the EOS M280 laser metal sintering machine, a UDC, and it prints through powder bed fusion process, uh, more specifically laser sintering, um, which uses a laser to fuse metal powders together and build a CAD material, a CAD drawing layer by layer. Um, well, our goal is to streamline the hydrogen generation process and make it more efficient by printing out merging steel samples and performing some post-processing test techniques. We intend to use Electroless nickel-based coating on these 3D printed metal components to enhance the part's ability to hydrogen to produce hydrogen, or potentially enhance the part's ability. And this will be done through water splitting, as Nofun mentioned earlier. Traditional water splitting uses a setup composed of an electrode uh, in a with an electrode, as in both a cathode and an anode, submerged within some electrolyte. One of these participates in oxidation, while the other is responsible for reduction. And coating AM metals with nickel is one of many ways to enhance the metal properties. The coating provides increased corrosion protection, it improves the surface roughness, and it increases the strength and durability of the material. For this, we have printed three samples, a lattice sample, a hollow cylindrical sample that was encased within the lattice sample, and just a plain square sample. And these will be coated through three different methods. Sorry, this will be coated through nickel with three different phosphate concentrations, low, high, and medium. Uh, and nickel deposition, electroless nickel deposition, is often known as deposition through chemical reduction, which in a second you'll find out. And the nickel deposition process is a purely chemical process in which a sample is placed in a nickel solution composed of either a low phosphorus content nickel solution, which has about 2 to 5% phosphorus, medium phosphorus, which has about 6 to 9%, and high phosphorus, which has about 10 to 13%. And when this nickel is heated up to an ideal temperature, for which low is 90 degrees, medium is also 90 degrees Celsius, and high is at 85 degrees. Uh, and just as a notion, phosphorus content is proportional to deposition rate. So in other words, for high phos deposition, we will be depositing nickel at a low deposition rate. For low phos deposition, we would be depositing nickel at a high deposition rate. So keeping all of these at a constant temperature will probably give us different rates of deposition, which we'll see in a second. And earlier I mentioned that nickel deposition, electroless nickel deposition, is deposition through chemical reduction, and you can kind of see it better here, where the sample is placed in the mid-phos solution, and as you can see, the solution is eating off some of that excess roughness, some of that surface, some of that metal surface, while simultaneously depositing nickel onto the sample.
So after we designed the electrode, and in order for us to prove our concept, we needed a way to measure the hydrogen produced. So one of the method and the technique is cyclic voltammetry, where we have uh, we pretty much sweep voltage across our working sample for testing, and this sweep will produce what some type of uh, this method use electronic voltage sweep across our sample in cycle, and the setup that we use is the one we have. So we have our potentiometer, and we have our electrochemical cell, and the connection of the picture in the bottom here, where we have the green is our working electrode, which is where our sample will be connected. And we have a counter electrode, which is a platinum in this case. And the role of the platinum pretty much is to close our circuit. So This will allow us to have some type of curve, some type of graph between the voltage that we sweep across and also the current that our sample produces, and we use that curve to measure our hydrogen production, as we can see in how we use those calculations next. So that this is our actual setup of uh, our electrochemical cell. So we can see that, as mentioned previously, we have our working electrode in green, and we have our also our counter electrode. Counter electrode here, which is the platinum, and uh, problem if our working our electrochemical cell here is that we had a size constraint because our electrochemical could only be connected with 1 centimeter cube sample, a centimeter square sample. And if the sample is smaller or bigger than that, we run into leak or problem to fit the sample in. So for our lattice sample, as we can see in the right figure here, we run in this problem. So we had to improvise and take our platinum electrode out of the electrochemical cell and submerge all the sample and the platinum counter electrode into some type of beaker or container and be able to continue with our measurement. So this is one of the issues we run into. Next.
In order to streamline this process, we'll be using an L9 design process. And for this project to be successful, we need to understand the most efficient method of hydrogen generation. This is the best way of doing that. And the design of experiment involves testing on a variety of different electrodes, and each with its own factors. In this case, 4 factors, each factor with 3 levels. And its Taguchi design of experiment is often referred to as offline quality control. That's because it's a method of ensuring good performance in the design stage of products or processes with not a without a an absurd amount of testing. For our 4 factors, we briefly spoke about the shape earlier with our lattice, hollow, and square sample. We'll also be submitting these samples to some sort of surface treatment, in this case, chem polishing, plasma etching, or none. Chemical polishing, similarly to Electroless, is a purely chemical process in which a sample is placed in an acidic solution, and during this process, the acid will smoothen the surface of the sample. As for plasma etching, it's an activator. It prepares the sample for deposition, making it more accepting of any deposition that would go onto the sample. It's also a method of eliminating corrosion, uh, as well as a smoothing surface. Uh, and as previously mentioned, the samples will be going through low, medium, and high nickel deposition. And the samples will also be going through a nickel strike process, which is also a surface activator. But in this case, it activates the surface to make it readily accept any nickel deposition that would happen. So we're looking at the variation from the 15, 30, and 45 seconds, and potentially how much nickel that would allow us to generate. And on the right there, you can see the plasma etching and chemical polishing processes. Uh, on the right here, you can see our design of experiment array. In other words, how the experiment's going to unfold. All image analysis will be done using the uh, Keyence digital microscope and the phenome scanning electron microscope. The Keyence microscope uses light to identify the surface microstructure of any samples that you might have. And the phenome electron microscope uses electron beams to see the surface of your sample. In this case, this is important because with chemical polishing, um, the sample might be extremely, extremely bright due to the reduced surface roughness. So if you use the Keyence digital microscope, uh, the light that's emitted might not show you some of the surface characteristics that the phenome electron microscope might. So we'll be seeing the difference between these. Results and analysis. Uh, we'll mainly be looking at the roughness analysis of these samples. And as previously mentioned, metal 3D printing has a plethora of benefits. However, one disadvantage is usability. Metal 3D parts are not perfect. Unlike traditionally manufactured parts, they cannot be printed and just put into use. So we'll be chemically polishing these samples as previously said, and this will give us an idea of whether post-processing techniques can affect the hydrogen production in this case. We'll be mainly looking at two different methods of analyzing surface roughness, RA, which is line roughness, and SA, which is surface area roughness. In line roughness, you can see in the image above, we have 6 lines, 3 vertical, 3 horizontal, and we'll be measuring the average roughness across all 6 of those lines in order to get a general idea of the roughness on the sample. For our surface roughness, that will just take the surface as a whole rather than in 6 lines. Um, and these were some of our results. For the polished versus unpolished square sample, mind you, some of these square samples were already extremely smooth, not from the printing, but from a previous experiment, meaning that we could only test on a specific area in the sample. For this area, we looked at it and we saw some roughness, some abnormalities on the sample. And once we polished the sample, it's completely smooth. This was the same for our polished and unpolished hollow sample, which is much more clear. I like to say that with the unpolished sample, you can almost feel the roughness just by looking at it. And that's evidence here with the 3D imaging. But once the sample is polished, it becomes completely smooth. And this is evidence once again for our lattice sample. Before it's polished, extremely rough. After it's polished, it becomes extremely smooth. And these are some of our results. In our results, across the board, we had a 50% reduction for line roughness of the square sample and significant reduction in all tested sample. We looked at a few different parameters, RA, RZ, RT, RQ. RA is the arithmetical mean of the samples, the 6 lines that we got. RQ is the root mean squared standard deviation. RZ is the elevation of the sample, and RT is the uh, peak to valley ratio, I believe. And looking across the samples, counterparts are placed line by line. So you can see for the unpolished lattice structure and a polished lattice structure, and the hollow sample as well, just significant reduction across the line. This moves us on to our electrolysis nickel deposition. These are our deposited samples, and there is a consistent level of deposition on almost all the samples. However, despite it being slightly clear here with the high deposition, as you can see, it's deposited, but it's not as reflective or as clear as the mid deposition. And for the low deposition, it kind of seems like same sample. That's because we ran into a few problems with the low deposition. Low Phos solution is known to be relatively volatile and hard to cope with. It is prone to overflowing, pouring out of the beaker, and understand it's poured out of the beaker many times before reaching its ideal deposition temperature. Due to this, our Electroless sample improperly deposited, which you'll see in a second. And when it did deposit, it did so at an irregular rate. So we went to the SEM to see how these affected our solutions. As you can see with the high Phos deposition, it seems nicely deposited, but not as much as the mid Phos, which, as mentioned, has a higher deposition rate, which seems almost overly deposited. However, with the low Phos, it seems as if the sample was almost scraped. As you can see, there are some areas that haven't been deposited properly. This is evidence for our hollow sample as well. For our mid Phos on the far left, Once again, seems like it's almost overly deposited for high Phos here. On the far right, less deposit, and far um, low Phos. Seems like we're missing some areas of deposition, some holes, some voids. And this is the same across the board for SEM samples. This is our elemental identification, or the elemental composition of the samples for our lattice sample. For our high Phos, we had a 14% phosphorus content, which is relatively consistent. However, one problem that we had across the board was that some of our samples oxidized. And I think Nofu will mention the electrolyte solutions that we use for our cyclic voltammetry in a bit. However, one of them was sodium hydroxide, which is known to oxidize some samples when they are placed within that within that solution, that electrolyte solution. So this allowed some of our samples to oxidize and build up a bit of oxygen on the surface. For our mid Phos, still consistent with 8% phosphate deposition, 91% nickel deposition. And for our low Phos, uh, this is what we meant about the difficulties when it came to deposition. As you can see, we had 67% nickel. The majority was
See what
oxygen.
I can do.
Our phosphorus content was at 8%, when for low Phos it should generally be around 1 to 3%, maybe 4. And somehow we got
Yeah.
carbon in there too. So it was just all over the place because of the irregular deposition.
When you put on the website.
Okay. For analyzing our data, we needed to find some type of
You
baseline,
put the
what
zip
to
file, right?
compare our electrode hydrogen production with. So we needed a
No,
platinum
the zip
electrode
file. You need to
as
copy
a
the zip
working
file to
electrode.
put in the website.
Um, we used copper to coat a platinum solution that we had on.
I
And
send you the
this is
latest
we
one.
set up at the
I will
top
send you again, okay?
right corner here, where we have attached our copper at the anode, and we had another platinum at the cathode. And the platinum solution then um, is to be heated at between 70 and 75 degrees. And while we were heating the platinum inside, the copper was dissolving, and then we had the deposition of our platinum on the copper. And the figure in the bottom here show how the difference between the coated part and the non-coated part. So we have the shiny, which is a platinum coated, and the copper part at the left. And this one right here is the curve of the platinum versus platinum electrode. So we have a platinum at the working side and a platinum also at the kind of electrode side. And which is will give us our baseline. So the figure here we have uh, to identify the peak current for the anode and the peak current at the cathode as well. And we use those uh, peak current to calculate our hydrogen produced. So we grouped our data in with regarding the three different phosphate level that we have. We had a high phosphate nickel solution, and we have a medium phosphate nickel solution and a low. So those three graphs are for our allo sample that Babakar mentioned,
Got it,
and we
right?
have our lattice sample, and we have our square sample. And when we look at the graphs, the voltammegram of those sample here, we can see the difference between those
Okay, what
three.
about
And the lattice sample had
the
a
one for
high
certificate?
peak,
Did you look
which
at that
means
one
high
too?
current peak at the
Hello.
cathode, which will allow us to calculate our hydrogen, followed by the hollow sample,
No,
and then the
the
square
one with the
sample was a
certificate.
little bit lower. And also for the lattice sample, we
Did you
had
get the name
our
of the guy?
voltage was low, which is a good sign because we needed, that mean that we introduced less power
Yeah,
to
yesterday, last night.
reach uh, the peak here. Next,
I share that
for
again,
the
okay?
medium sample, medium phosphate, we have the same trend also.
Yesterday.
where we can see that our lattice
Send me
sample
the information. See, I
showing
can
a
correct it
high
if
peak,
you want to
followed
correct it.
by the hollow, and then the square sample again. Next.
Okay.
And for
Okay.
low phosphate, we can see that um, our lattice sample is higher, but um, our hollow sample and the low phosphate are almost the same. This is due probably to the low phosphate deposition and rate, and this is kind of like thrown off the result for the low sample here. Next. So how do we really measure our hydrogen production? We have a voltammogram here where we can see that at the high peak here, which is the cathode side, we will have our peak current, and at the low here, we will have our peak current for at the anode, which is the oxidation part. So we use the equation, for example, for the solution, electrolyte solution NaOH that we have. And what we retain here is that we have a stoichiometry of 2 here for the hydrogen production. And we need that in our calculation using the Faraday equation, which links our peak current to our number of mole. And also we need the ideal gas uh, law equation, which link our volume to our number of mole. And using those two equations, we are able to calculate our volumetric rate, and using that equation here, and we have the result compiled in the next slide. So for sodium chloride, those are our L9, and we can see that the lattice sample here for our L2 had 11.15 standard centimeter cubic per minute, which is our unit that we use. And also we can see that our L L6 here has some type 5.78, and this also is reflecting in our graphs here where our L2 had the highest peak. Next slide. And then we have our result here using the sodium hydroxide, and we can see that also our L2 had a higher peak compared to which is the lattice sample. And also, we can see that for the oxidation volume here, we had higher volume compared to the NaCl, hydrogen chloride. This is due to the fact that hydrogen hydroxide intend to increase the oxidation of ours in our anode, which is will increase the number of oxygen. So between the two electrolyte, I think NaCl is more prompt to not um, add oxidation to our result. Next. So in conclusion, we made we were able to produce our electrode and measure the hydrogen production. And we found that the lattice structure presented best result for both the sodium chloride and the sodium hydroxide. Between our type of deposition, the deposition that we use, we see that the medium phosphate treatment on the sample present the best peak evolution and gas production at the reduction of electrode site. This could due to the ideal deposition circumstances. So comparing our result to our baseline, which is platinum, we can see that the lattice sample produced 6.87 centimeter cube per minute of gas compared to our platinum, which is a good result if we take in consideration how costly is the platinum compared to our steel margins steel. Like for example, at the marketplace right now, the platinum is pretty much $39 per gram, where our steel is 7.26. So if we are able to produce electrodes, just print them using, still we really saving because of our production.
And this was a proof of concept study. In other words, we're generating these results in order to work on future research opportunities with it. This can be from fuel cell research to photocatalysis, which was the original motivation of this project. And realistically, any project that has any significant hydrogen production or harnessing aspect onto it. With more time, we could have performed research on a much larger DOE with a wide array of unconventional electrodes, which was originally the plan. However, things in research don't go smoothly. We faced a lot of challenges and failures, including the challenges placed upon us by COVID restrictions, our electrode design restrictions. We wanted to print more samples. However, the metal 3D printer is running into some problems, so wouldn't have been time efficient to print. Some project direction changes and our failed plastic electrodes. As Nofu just mentioned, the price of platinum and other noble metals such as gold uh, is up there. It's skyrocketing. Uh, and our goal is to streamline this process and make hydrogen generation an affordable method of energy storage. So we tried to print plastic electrodes using the Losbot TAS 6 printer. Um, in order to streamline the hydrogen generation process. That way, if we have a plastic electrode that we can then coat with electroless nickel, um, easy money. Then we could just put it into production and try to generate hydrogen, store it, and move forward into a more sustainable future. However, we experienced some problems with our failed electrodes. For one, the solution was too hot, being around 90 degrees Celsius for low Phos. And the plastic electrodes just couldn't handle it, so they started to deform. However, this is another opportunity for future research, as there are some methods of coating plastic electrodes into metal. We can see how that can affect any hydrogen generation process. The researchers would like to thank our advisor, Dr. Palantiagi, who was a lot of help in this project. Just when we thought we were done, he helped us and asked us to look for more, to get more research, to refine the project, make it better, make it publishable. To our postdoctoral scholar, Dr. Eva Mutunga, who was a lot of help, literally spent 6 hours helping us with this presentation, which is a lot. Wendwison and Andrew, who are also post-bachelor's researchers, uh, doctoral candidates, I believe. They were a lot of help to our fellow students and professors and advisors, and to the University of the District of Columbia, and to NSF and NSA. Thank you. Any questions?
Good. Any questions from the audience?
I just wanted to make a quick comment. I've seen this presentation at least once or twice this semester, so it's nice to see the progression of students and kind of fine-tuning and refining their work and taking some of the feedback to heart. So I do very much commend you guys for improving upon your presentation and the results and how you presented the results. So nice work there. I guess I just have the same question that I asked, some of the earlier presentations. What did you find was the most challenging aspect of your project, and how did you overcome that?
We mentioned a few challenges and failures. I think the biggest challenge was in some of the data collection. Nofu mentioned how we use two different electrochemical cells. The AIMTech electrolytic cell that you've seen, and also just a container, an open container. That's because we ran into a problem with our samples. They were a little bit too small to fit onto the original electrochemical cell, so we had to improvise and then use not only the platinum electrode that we had for our sample, here, but also just an open container and our sample submerged within the container in order to get some results. So there are definitely some problems in the design that we had to, try and fix. Another issue would be in our platinum counter electrode. In order to see the best hydrogen generation method, we had to have a baseline study and have a sample that can cope with our platinum counter electrode. However, we mentioned this multiple times, platinum is expensive. I can't just walk around and buy a platinum piece somewhere. So we had to coat the platinum. Um, uh, and this was an experience because there weren't many guidelines onto how to coat the sample. We only had the coating solution and the copper piece. So we had to work along, try, fail. And eventually we ended up coating this copper piece with platinum in order to get our ideal baseline experiment. So some of those challenges were there and we had to go around them. And I think it was just a great experience.
One of the questions or something I'm wondering is might be worth pursuing, in the near future is some in situ type of experiments, because it seems like there's a lot of parameters that you have to adjust, especially during the deposition. With the Keyence microscope, which has a very large working distance. I mean, obviously in the SEM you can't do liquids, right? But in the Keyence microscope, which is an optical system, I'd like to, see if we can start to, integrate maybe some in situ type of experimentation, where we can monitor some of these processes to really try to optimize and see what's happening at the surface level, right?
Yeah.
As the process is going on. So, did you guys consider, doing sort of sequential imaging or something like that?
Yeah, originally we did consider going to more imaging. However, we ran into some problems with that as well. We wanted to compare the before and after of the deposition on the Keyence microscope as well. However, like mentioned, we ran into some problems with our L9, with our low Phos deposition. So we had to push that until we got the low Phos deposition. And by the time we got the deposition working or working ish, we couldn't go back to the microscope and compare and contrast. But yeah, that was an original part of the research that we were looking forward to. It just didn't materialize.
Okay.
Yeah, good. So I saw you mention that you have some failure with the plastic structure as electrode. Have you tried to maybe look for some other plastic-based, material that can sustain? I think you mentioned 90 degrees Celsius
Mm-hmm.
for the temperature. So there are some material available there. I can sustain much higher, like close to 200.
Yeah,
So maybe that's another thing you can, try to do,
yeah, definitely. We looked into different. I don't know if you want to take this, because I've been talking a lot.
Yeah, we looked into different type of plastic that we can coat just with our nickel sample. But by the time, this project was pretty much a two-step project. We needed to get the electrode and then test. So we're really limited by time, and we couldn't really go into deep in trying to find what type of plastic. So we had to do a 180-degree turn and try to just use the metal to get the project done. So that, yeah, we could have just tried to find different type of plastic that are available and that our printer can support.
Yeah, what I'm saying is that the printer you have, if you upgrade to a different material, because you're only looking at 90 degrees, so maybe there's ways you can print something that can sustain the temperature in your experiment. So yeah, so that's just maybe in your future work that can be an easy way for you to print different structure compared to using a metal piece. Yeah. All right. Any other comments or questions?
Yeah, Dr. Pant here. I had the opportunity to review the final draft. Definitely after some corrections with language and all that, and the presentation really came out well. Definitely congratulations to all of you guys.
Thank you.
Definitely read well and they came out well. Yeah. I like the whole thing. Yeah, thank you.
Thank you.
Yeah, sorry I joined a little late. Late means like quite late. I was in the metro and just happened to end up here. So yeah, congratulations, Nofu, Babakar, Eva. I think you guys did very good, and yeah, we look forward to making good use of your work. Thank you.
All right. Thank you, Dr. Equi.
Okay.
Okay. Any other questions or comments from the audience? All right. If there's no other comments, again, congratulations and to all the seniors here presented today. And also congratulations on your completing your project and graduating from this program. And you all did a great job, overcoming all the restrictions because of COVID and also, all the challenges of timeline and everything. Yeah, I hope you continue our success wherever you want to stay at the UDC for your graduate program, or you want to continue on for another, journey. We wish you all the best. And before I let the audience leave, I also want to mention that all these projects you have seen today, all thanks to our all the centers and grants we received from national federal agencies such as NASA, NSF, the DOE, and all those funding support enabled us to support your project and also provide the support for the resources you need to make your project successful. So thanks to all the federal sponsors to our program. And I think this afternoon we have a award ceremony for the graduating students. So please join in the afternoon at 4 o'clock. I think with that, I think that's everything we want to cover for today's presentation. And I think we're right on time. So yeah, so if there's no other further questions or comments, I'm just going to end here. And I wish you all the best for the remaining of your spring semester here with us. All right, thank you.